ضمير السؤال هدول كمان ده.
شغال برزنتيشن؟ لا شغال هذا لا مو شغال.
First of all, did you upload your presentation and presentation to the related part of the Blackboard?
Uploaded
Only the report.
The report only.
Only the report.
Yes, he said.
Okay. After it, I mean, within 24 hours, okay?
We should.
All groups should upload your presentations too.
Okay.
Got it?
Okay.
Yes? From each group member, only one person. You actually uploaded the thesis.
Yes.
Also, presentation.
Okay.
Got it?
Okay.
It can be in PowerPoint or whatever, PDF or whatever. Okay, but you should actually
Sure.
upload it.
duplicate محطوط أو فقط.
Yes. Can.
Bu çalışmıyor. Tamam.
أنا بحكي بالعربي مرات رح أقول لك ارجع لي اسم الملخص هون السلابس. هون لما يجي عندي البيمز، هون عندي البيمز رح ترجع لي لورا، بس تقرأ كلمة بيم ترجع لورا لعند مو لورا لعند البروفايل. هلا أنا بقول لك
Lan işte
يس.
شغال.
Yes.
Can you please turn off the lights?
We start?
Yes.
Good afternoon, everyone. My name is Zaid, and this is my partner Ahmed.
Thank you.
Our assigned subject for our graduation design project was reinforced concrete, and we chose our topic as a 5-story reinforced concrete building. Our project was supervised by Dr. Ondar Umut, and he supervised every step of the project. Please go to the next step. So here, the introduction. The purpose of our project, we wanted to design a dormitory building, and it will be in Chile for the students of Ishik University, because as we know, Ishik University is in a area away from cities, so most students live more than 20 kilometers away, so there will be high demand on students who want to live in dormitories because the prices of the houses are expensive. So we wanted to make a dormitory building in Chile, and it will have high demand because Ishik University is in a very isolated place. It's not in a big city. Throughout this presentation, I will talk about the social impacts of the project. We will talk about the work plan, the structural design and analysis, and the regulations which we use. These are the Turkish standards that we used throughout the project. Also, I want to mention that throughout this presentation, we use knowledge that we obtained from courses like computer-aided design for plant drawing on AutoCAD. We used knowledge from soil mechanics, from foundation engineering to choose the type of foundation we want to design. We also used knowledge from Structural Analysis 1 and Structural Analysis 2 courses. And for the modeling of the SAP building, we also used knowledge from the computer-aided structural analysis course taught by Dr. Onder and Dr. Bora. Please go to the next slide. So we have 5 stories in our building. This will be the ground floor plan for the first story. Here we have, this will be the entrance to the building. There's a waiting room, there's a gym. Here we have stairs, an elevator. This is a laundry room, a storage room. This is the kitchen. This is a dining area, and there are toilets. This is for the ground floor. From floors 2 to 5, as I said, it's a dormitory building. We will have 10 dormitory rooms. Each room will fit 3 students. Each room has its own bathroom. Again, the stairs and the elevator. So since each room will fit 3 students, and we have 10 rooms, so that's 30 students per floor. And since we have 4 floors, 4 room floors, we will have a total of 120 students that are residing in this building. And we expect that the building will be full most of the time because of the high demand on accommodation in Chile. Please move to the next slide. Now I will talk about the social impacts of the project. So the economic impacts are that it reduces student housing costs through optimized design, long-term saving via energy efficiency. The environmental impacts are that it minimizes carbon footprint with recycled concrete and energy-saving systems. The health-related impacts are it promotes well-being with noise reduction design and natural lighting. And for safety-related impacts, it has validated resilience via TBDY 2018 compliance and fire-safe egress routes. This is the code that we will use for earthquake. And for the social political impacts, it eases student housing crisis while adhering to urban development policies. For ethics, it ensures fair labor practices and safe dormitory conditions for residents. And for sustainability, it targets resource efficiency, for example, rainwater harvesting, for reduced operational waste. And finally, for manufacturability, SAP 2000 identifies constructability challenges early, ensuring alignment with Turkish material standards. Next slide, please. So this is our project work plan. These are the 14 weeks of the semester. This is our starting date, our finish date. It took us about 3.5 months. Our first project phase was plan drawing. We did that on AutoCAD. And then also after that, we did the slab thickness calculation, determination of vertical loads, i.e. dead and live loads. Then we did the reinforcement calculations for the slabs. Then we created the finite element model on SAP 2000. Then we did the pre-sizing of columns, beams, and shear walls to ensure that our original dimensions that we started with are sufficient to withstand all loads. After that, we determined the earthquake loads. We did beam reinforcement and stirrup calculations, column reinforcement calculations, and finally we checked irregularity control, earthquake regulations, and we did the foundation modeling. Finally, we did the cost estimation. It is worth mentioning, go to the next slide. It is worth mentioning, since our system is symmetrical, it is very unlikely that we will have any torsional irregularity, but we will check for torsional irregularity later in the slides. As you can see, we were inspired by the earthquakes that are happening in Turkey. So we wanted to build an earthquake-resistant building. So we included shear walls so they can resist the shear forces of the earthquakes. Here, our original column dimensions. So all columns were 35 by 70 centimeters. The beam width was 25 centimeters. The beam height was 50 centimeters. Our shear walls in the X direction, so this one and this one, it is 4 meters by 30 centimeters. And for the shear walls in the Y direction, it is 2 meters by 30 centimeters. And this is the plan before the pre-sizing calculations. Next slide. Next slide, we will talk about slabs, and Ahmed will explain slabs.
Thank you. As you know, every building contains of slabs, beams, columns, shear walls. So elements in this slide, in these slides, we will show the calculations, the reinforcements, how did we obtain all the parameters. So at the beginning, we will talk about slabs. We will find firstly the thickness of the slab. Secondly, we will determine how much vertical load acting on the slab. After calculating vertical load, we will calculate the moment, and finally we will use the value of those moments to find how many rebars needed for each slab. So at the beginning, we are going to calculate whether each slab from those 9 slabs, whether they are one-way slab or two-way slab. And this is the formulas that is being used. For those slabs, 1379, 1379. We have this, the longest length, and here the shortest length, this length. And after dividing both of them, we will find the parameter m. If it was more than 2, that means our slides is one-way slab. If it was smaller than 2, that means our slabs is two-way slab. So after doing all of those for all slabs, we will find that all our slabs are two-way slabs. Since all our slabs are two-way slabs, we are going to use this formula to find the thickness for the slab. As you can see here, m value is obtained. This is the shortest length net, which is this length from here to here, from here to here, from here to here. And lastly, this alpha s, which means some of the lengths of the continuous edges over slab circumference. Here, as you can see, we done this formula for all slabs. We obtain those values, and by putting those values in this formula, we obtain those thicknesses. As you can see, the most critical thickness here is 15 centimeter. To be more in a safe side, we took all the slabs thickness as 17 centimeter. Okay. After we found the thickness for each slab, now we need to find the vertical loads. The vertical loads is, as you know, a combination between a live load and dead load. So dead load for each slab, I should mention that we divided our slabs into two categories. First of them, stairs and elevators. Second of them, room slabs. So for room slabs, we have some materials that is on the slab, which is plaster, marble floor, coating, C30 concrete. So here's the unit weight for each of them. And like, for example, plaster, we choose to put 2 centimeters on each slab for room slabs. We obtain those values by timing this times this equal this. So here for room slabs, this is the dead load. For stairs and elevator, this is dead load. For live load, it's from standards, Turkish standards. For rooms, it's equal to 2 kilonewton per meter square. And for stairs and elevators, it's 3.5. Doing under this combination, we will find the design load for each slab. Using the value that we obtained before, the vertical load, we will plug it here, and shortest length, which is shown in the plan view. We have only to find these coefficients using this table. We will find the moment acting on each slab. We will find this moment in both places. Firstly, at supports, which is the place near to the beam, and second one at the openings span. It's almost in the middle of the slab. Using those equations, we obtained those values. So this is the moment values for at span and at supports. After we found the moment, now with the last part, we need to find how much rebars do we need for each slab. In order to find this, this is the formulas that we used. Briefly, first formula that we used, this formula, we will obtain out of this formula this Km value. From Km value, plus knowing that we are using concrete class C30, we will obtain Kz value. From Kz value, we will obtain, using this formula, we will obtain AS. AS, which means cross-sectional rebars area. From this cross-sectional rebars area, we will determine how many rebars do we need to use. But there's a control we should do first. After finding this area, we will find the minimum area according to the regulations. We will compare between them. We will take the greatest value. After this, we will calculate the S maximum spacing between rebars. And from those, we will find the rebars. But we are going to find the rebars for both at openings and at support. So this is the procedure that we are going to follow in order to find the rebars at the openings. And this is the procedure that we are going to follow when we are going to find it at supports. It's almost the same procedure, only there is one step before. When we are going to find at supports, there is both plan view. Let me show you in plan view. In plan view, so at supports, as I said before, slab here there's slab D101, 101, and here there's slab 102. Both of them, they exert moment to this beam. So here's support, here moment 1, moment 2. So we are going to divide the maximum, the minimum moment over the maximum moment. And if this value was greater than 0.80, that means no need for correction. If it was lower than 0.80, that means correction needed. And this is the formula used. And after finding the moment, we will follow again the same procedure here. Let me show you. So this is just an example. We all the details is shown in the report. This is just a detail, small detail to show you. For example, for slabs 101, 103, 107, 109, as we did before, this is the formula. We plug the values, we find Km. From Km and C30, we find Kz using that table before. Using this Kz value, we find the cross-sectional rebar area, and we will take the greatest value between both of them. That means we are going to take this 300 millimeters square. And after finding how much space between each rebar, we got to conclude that in those slabs, we are going to use 10 rebars, and the diameter would be 20 millimeters. Yeah, here it's shown. Here, the same we are going to do the rebars for Y direction and X direction for each slab. Y direction and X direction. After we did it for Y direction, we find this. After we did it for X direction, we find this. And here's the conclusion. For those slabs, this is the number of rebars needed, this is selected diameter, and this is total rebar area. This is, we are doing it at openings, at span. Now we should do it for, after these slides, we are going to do it with support. Go to the next slide. Yeah, here, as I said, we did it for openings. Now we will do it for support. Again, same procedure here. We follow, and we find here we don't need rebars because it's sufficient already. Here we need this much rebars, and this is the conclusion. For this slabs, we need to find this much of the rebars. Now we continue.
So as I said before, we decided that our building will be in Chile. This is Chile, and this is where our building will be. This is the plan that we modeled. Again, I emphasize that the shear walls are very important for resisting earthquake loads. Next slide. And this is the modeling of the building on the SAP 2000 program. We used C30 class concrete. 30 here refers to the characteristic compressive strength of concrete, which is measured after 28 days of mixing. And it is measured in megapascals. We also used class S420 steel. The story height between each story is 3.2 meters. During the modeling of the building, we would first start by assigning frame sections like the columns and the beams, and we also do area sections like the shear walls and the slabs. Next slide. Now we will talk about the pre-sizing calculations. First, let's talk about the pre-sizing calculations of the column. So this is our original plan with dimensions 70 centimeter by 35 centimeters. So the cross-sectional area of the column will be approximately 245,000 millimeters. Next slide, please. So here, to do column pre-dimensioning, we have to use this formula. This is the critical cross-sectional area. This is the normal force values that are acting on the columns. We obtained these values from the SAP 2000 model. And this is the characteristic compressive strength of our concrete. It will be equal to 30. So here we start 0.4 times 30 is 12. And this is the value that we got here by plugging in the normal force and 30. This is the critical cross-sectional area that we need for the beam. And then we will have correction factors. So normally, in a normal system with no shear walls, the correction factors will be 1.5 for side columns, 1.7 for corner columns, and 1.3 for inner columns. But since we have shear walls in our system that will help carry some of the loads, some of the normal forces, some of the loads on the columns, we are using these correction factors. They're a bit less than these correction factors, but we have shear walls in our system, so we will use these correction factors. After multiplying this cross-sectional area by 1.5 for corner columns, these are corner columns, we will obtain this minimum cross-sectional area. For side columns, we multiply by 1.35. For inner columns, we multiply by 1.2. So our original dimensions for all columns were 245,000. And here the critical area was, I believe this is, yes, 114,836. So it was not sorry. Yes, it was not sufficient. So we had to. I think there's a mistake here. There should be. Okay, it was 114,000 millimeters square, which was not sufficient. So we had to change the. Sorry, I think there's a mistake here.
I think here was sufficient. The first one, second one, and third one wasn't sufficient. So we
Yes. The third one wasn't sufficient. I'm sorry.
third one only wasn't sufficient.
Yes.
So because of this third one, we changed all of them to be sufficient, all of them.
Yes, so our new dimensions are 350 by 400. This is 140,000, which is greater than 114,000, so this is okay. We selected these new cross sections, so 350 by 450, it is 175,000, which is greater than 174,000, so this is okay. And 350 by 950 is the new dimension of the inner columns, and it is equal to 323,500 millimeters square, which is greater than the critical cross-sectional area. So this is satisfied. So we'll have these new column dimensions. Okay, next slide, please. Now we will talk about the beam pre-sizing calculation. So for all beams, we have this condition that must be met. So the beam width should be equal to or greater than 250 centimeters. Our original beam dimensions are 250 centimeters for the width, so we don't have to change the width. Now for the outer beam size calculations, these are the span lengths, and this HK value represents the height of the beam, and we will calculate this HK value. So for outer beams, we will divide the span length by 15. So by dividing 4.88 by 15, we get 33 centimeters. 5 by 15, we get 34, and so on. For the inner beams, it's the same thing, but we divide by 12. So we should have the beam height at least for this beam should be at least 67. For this beam, at least 66. For this beam, at least 42. But since we want to make the calculations later easier for beam rebar calculations and beam stirrup calculations, we decided to take all beams, we'll give them the same height. So we gave them all 70 centimeters, which is enough. So our original beam dimensions were 25 by 50 centimeters. So the height was 50. Now it will be 70 centimeters, and it satisfies. Next slide, please. Finally, for pre-sizing calculations, we will talk about the shear wall pre-sizing. First of all, we have these conditions that also must be met. So the H value, which is the thickness of the shear wall, it should be greater than 25. For all shear walls in our system, the thickness was 30 centimeters, so it satisfies this first condition. Also, the H value should be greater than the story height, which is 3.2 meters, divided by 16. So here when we take 320 centimeters or 3.2 meters divided by 16, it is equal to 30, which is greater. I'm sorry, it is equal to 20. And since our h is 30, 30 is greater than 20, so it's okay. And this is for both shear walls, the ones on the x direction and the ones on the y direction. And finally, this condition is what differentiates shear walls from columns. So if b over h, so the length of the shear wall divided by the thickness of the shear wall was greater than 6, then it will be considered a shear wall. If it was less than 6, it would be considered a column. So the length of, let's say, the shear walls in the x direction, this one and this one, is 4 meters. So we divide 4 meters by the thickness of the shear wall. So 400 divided by 30, it is equal to 13.33, which is greater than 6. It's definitely a shear wall. And for the shear walls in the y directions, the length is 200 centimeters. So we divide 200 by 30. It's also 6.67, which is greater than 6. So it is a shear wall. Also, we have to use this formula to find the critical cross-sectional area. The normal force values acting on the shear walls that we obtained from the SAP 2000 program are here. FCK is equal to 30. So this is for the x direction shear walls. So this one and this one, they're symmetrical, so they will have the same value. Again, for the y direction shear walls, they're symmetrical. All of them will have the same value. So at the start, let's calculate our original dimensions cross-sectional area. So for the x direction shear walls, it is 30 by 400, or 300 millimeter by 4,000 millimeter, which is equal to 1,200,000 millimeter. And for the yes, and then after we plug in this formula, the normal force that we got from here, from the SAP model, FCK is equal to 30, we will find that the critical cross-sectional area is 189,000 hour enough, so we don't have to change it. For the y direction, we just plug in this y value for the n. And again, our original dimensions were 30 centimeters by 200 centimeters. When we multiply to find our cross-sectional area, it's 600,000 millimeters square. The critical is 189,000, and since our original dimensions are greater, that means they are sufficient. Next slide, please. Our plan view after we adjusted the sizes of the columns. So now the inner columns are 35 by 95 centimeters. This is 95, this is 35. The side columns, 1, 2, 3, 4, 35 by 45 centimeters. For the corner columns, it's 35 by 40 centimeters. And the shear walls, we did not change them. We didn't have to change them. They're the same. And the beams, we only changed the height of the beam. Excellent. Now we will talk about earthquake. Ahmed
How
will.
many slides remain?
It's totally 49 slides. I think we're halfway through.
Half.
Yeah, I
Yes.
think.
We have a big lack of time. I mean, it's approximately 1 hour.
Yes.
Can we skip to the important parts? Of course. Skip to
Yeah,
the
we will.
important parts.
We will do it faster. Is it okay?
Okay.
Okay.
Within maximum 10 minutes or 15 minutes, finish it. Within 15 minutes.
Okay, we're gonna try.
For earthquake,
As you know, our building is. We are planning to construct it in Şile, which is in Istanbul, and which is in Turkey, as usual. So, as you know, in Turkey, Turkey is located in earthquake zone. This is why we should construct our building accordingly, which means we should make sure our building is being constructed satisfying the regulations. Since we are using a coupled shear wall building, so we will have this R value and D value. From those values, we are going to find RA, this value. Those values that we obtained from those tables, we are going to show how it's benefit.
5 and less than 1, we will use this formula for SAE, which we will use in SAR, which in turn we will use later on. For SAE, it's SD1 over the period, so equals this. SAE on the y direction, it is equal to this. Then for SAR, it is equal to SAE over R. R, we got it from the table before as 7. G here is the gravitational constant, 9.81. We will find VTE and VTE minimum. So VTE is equal to the mass of the building. We obtained the values of the weight of the building from the SAP 2000, and then we divide them by the gravitational constant to get the mass. The total mass of the building is 2,177. So this is empty. SAR, we'll do it once for X, once for Y, we'll substitute in. For VT minimum, again, the mass of the building, I is the importance factor. We got it from the table before as 1, and SDS also from here. We calculated the VTE and VTE minimum, and we should have that VTE is greater than VTE minimum, so it is okay. Again, for Y direction, we do the same thing. And then we will, using the VTE value, we will calculate delta F and E. N here is the number of stories that we have. Since we have 5 stories, we use it as 5. VTE value we found here for X direction. For Y direction, it's this one. We substitute, we find F and E. Then we will VTE minus F and E to get these values, which we will use in the table in the next slide here. We will use it over here. This is the last one we found. So this is for X direction. These are the masses of the building. This is the story height from the ground, 3.2. It increases by 3.2 for every story. We multiply this by this to get this column. And then we divide this value by the summation of this column to get this column. And finally, this column is this part, and this part is this part that we found in the slide before. By multiplying these two, we will find the earthquake forces that are acting on the X direction. Please move to the next slide. Next slide. So these are the earthquake forces that are acting on the X direction. For the 5th floor, we have to add the value of delta F and E for the 5th floor. And then for the other floors, it will be the same values in the table. For the shear force on each floor, it will be this value plus this value for the 4th floor, and then plus this for this, plus this for this, and so on. In the Y direction, everything is the same. The only thing that is different is this value, which we will substitute here, and we will get these forces. Again, these are the forces on the Y direction, and these are the shear forces that we obtained in the same manner. Now, Ahmed will explain the beam.
Can explain in general.
Yes. In general.
All the values, okay?
Oh, okay. In general.
Explain it and
In general, okay. After we found earthquake forces, now we are curious about beams rebars calculations. We need to find how each beam contains, how much rebars contains. So here's the procedure that we are going to use. As you can see here, we have equation 1 and here equation 2. And this moment we obtained from SAP 2000. Using equation 1 and equation 2, we will find the area of rebars tension. It's unitless.
Is it a coefficient?
Yes, it's coefficient. Rho means yes. This rho means ratio of tension rebars area within the beam. It's just a ratio. So we will use this and this in order to check whether our rebars ratio is sufficient or not. So this is a constant, both of them. We will find tension rebars and compression rebars. This is tension rebars. After doing this formulas and this procedure, we should select for each beam 3 rebars. The diameter would be 16 millimeter. After this, we go to compression rebars. From the same procedure, we will find that mostly all the beams that we are going to use 3 rebars with the same diameter, 16 millimeter, except those beams, those and those. We are going to use 4 rebars. Go to the slide. And here's the cross section. It shows what we said. For those beams, we are going to use 3 tension rebars, 3 compression rebars. Here, 3 tension, 4 compression. After this, we will go to stirrups.
We will follow this procedure for calculating the stirrups of the beams. If VD is smaller than VCR, then we will use S max, which we calculated here. If VD is greater than VCR and less than Vmax, then we will find VW, and from VW we will find the spacing, and then we will apply these conditions. Next slide. So, for example, for these two beams, the VD value is over here. It is less than VCR. So we will use Smax, and we will apply for the confinement zone, this zone. We will use these. So the maximum spacing between rebars should be 767, but it should also be less than 165, should be less than 128, and should be less than 150. This is the diameter of the tension rebars that we calculated in the previous part. So since it should be less than 128, we chose the spacing as 100 millimeters. As you can see here, this is for the confinement zone. So this is here and here. For the center zone of the beam, we have to, these conditions must be met. Again, our Smax is this. It should be less than 350. It should be less than 200. So we chose 185, which is 25 total stirrups. This is the center zone. Next.
These are the same. I think.
Yes. Yes.
They are the same. For columns, from SAP 2000, we found moment under envelope X, under envelope Y, and normal force under envelope X and envelope Y. These are the values. We are going to choose the greatest value acting on each column. As you can see, corner columns, side columns, inner columns. Since the greatest value is in X direction, so we are going to use this H, this lambda. By using those formulas, we obtained the following. I would like to mention that there is this parameter that we should calculate. And this parameter and this parameter. From those parameters, we are going to choose which diagram we should follow to find those parameters. At the end of this calculations and these formulas, we found that for corner columns we need to choose 6 rebars with diameter 18 millimeter, and here 6 rebars 20 millimeters, and hence 16 rebars with 18 millimeter. This is under X, and here in Y direction. We found the same values. This is the diagram that we used. For corner columns. This is for side columns. This is for inner columns. And now we will torsional irregularity.
Now for torsional irregularity, we will use this formula to, if this value is greater than 1.2, then we will have torsional irregularity. But of course, we don't expect to have torsional irregularity because our system is symmetrical. So this is the maximum relative displacement, which we find from the SAP 2000 program. So for example, this is the first floor under EXP loading. We'll take the maximum out of them. This is the maximum relative displacement. The maximum is this, the minimum is this. To find the average, we use this formula and we apply it here. We do the same for all of them. If it is greater than 1.2, then we do have, but as you can see, they're all less than 1.2, so there is no torsional irregularity. For the foundation modeling, we chose a matte foundation, also known as raft foundation. Because we have ZC class soil, the modulus of subgrade reaction is typically from 30,000 to 80,000 kilonewtons per meter cubed. I chose the middle value in SAP 2000 program as 50,000 kilonewton per meter cubed. The thickness of the slab is 50 centimeters, and it extends 1 meter in all directions. So this will be the foundation dimensions. Here we have the moments acting on the slabs, and what we can tell from these moment diagrams that we obtained from SAP 2000 program, we can tell that the highest moment is usually at the inner columns, and it is less at the side columns and even less at the corner column. These are under different types of loadings for X and Y direction. And finally, cost estimation.
This is the last step, cost estimation. In order to construct any building, you should know how much does it cost. And nowadays, the reinforcement concrete construction cost is approximately $250 for 1 meter square. Since we are constructing 5-story building with dimensions 15 meter times 24 meters for each story, and since we have a foundation with these dimensions, that means our total cost would be $560,500. And as you can see, this is a really expensive building. Go to the next slide. Honestly, our project finished in the previous slide, but this is an external. This is
Extra part.
extra work that we did to show you that there is a revenue estimation we did. As we said before, we are planning to construct a dormitory. Nowadays, the average cost for travel room in dormitory is approximately $2,500 yearly per person. So in each room we have 3. That means per room we will have $7,500 yearly. Since we have 5 residential floors, each having 10 rooms, that means in total we have 40 rooms. Total yearly revenue, 40 rooms times per room, $7,500. That means in 1 year we will have as a revenue $300,000. You might think that because this revenue we will take every year, that means within 2 years we are going to cover up from the high cost. But what can I say? No, it's not 2 years, it's not 3 years. It's gonna take it's gonna take more time since we have bills, we have extra work for workers. We should give them salary for architecture stuff. So that means it will take more time, but still at the end, this revenue is being expected to have this value to remain constant, since we are building in Chile, which there is a high demand from students. So
Also, you can say that the cost doesn't include the land price and architectural price.
Yes.
Only the
yes,
Only the
so yeah, that yes. So as I said, it will not cover this revenue. It will not cover the cost within 2 years. It's gonna take more time, but at the end, this project is profitable. If you think after 10 years, it will give you money. It will be profitable for you. I would like to thank every one of you for listening to us. Honestly, after doing this project, we learned 2 outcomes. First one, we get experience to use SAP, AutoCAD, writing reports.